No, I'm just like, I'm something about it.
All right, everyone, let's get back to our seats so we can begin the second talk of the evening. Peter holds appointments as a tenured researcher at CWI and professor at VU University Amsterdam. His academic background is in database systems with the open source Columnar MonetDB outcomes of his PhD. You may also know him for his contributions to X100 and Hyper, also known as the backing engine for Tableau. Managing vector data entails storing, updating, and searching collections of large multidimensional pieces of data. Some believe this justifies the creation of new class of data systems, such as PDX, or Partition Dimension Across. This talk gives a sneak preview of his ongoing work in this area. Everyone give a round of applause for Peter Boncz.
Thanks for having me. Very excited to be in New Amsterdam, as it was called. long time. Actually, here we are in Breukelen, which is a village to the south of Amsterdam. But okay, in the new world. Okay, so my name is Peter Boncz. I'm from the CWI. So the CWI is the Dutch National Research Center for Computer Science and Mathematics. It is quite well known for Python, actually, mostly, I think. Dijkstra was also there, so Python was created in Amsterdam. And our own group, has developed, it's called the Database Architectures Group, has developed various database systems. In my PhD, as in the introduction, I worked on this MonetDB, which was the first analytical column store. And later, on a second system, like 12 years later, we started a new system. It takes a lot of time to build a database system. Vectorwise, which introduced vectorized query processing as a technique to do efficient query evaluation. And that technique is basically everywhere by now. And 12 years later, we started a new system called DuckDB, DuckDB, which you probably know. And this is a very popular system. It was created by my colleagues Hannes Mueijsen and Mark Raasveld. Mark was the first PhD student of Hannes. And they are now the respective CEO and CTO of a company called DuckDB Labs. The idea is to make analytics fun and easy to use. So it's really a system that tries to make to work on user friendliness in analytics, pairing it, of course, with high performance and state-of-the-art techniques, because performance is also a part of user friendliness, but it's by no means the only part. And so this is a very, very popular system with 30 million downloads, I think, last month or something like that. So yeah, what is DuckDB? It's a column store. It uses vectorized query processing, stores data in a single file, uses the Postgres parser, is implemented in C++, and uses MVCC, so multi-version concurrency control, and art indexes. And here are some of the logos that you may see flying around. The DuckDB logo. DuckDB Labs is the core team, so that's where Hannes and Mark are, the CEO and the CTO of DuckDB. This is a relatively small company that really develops DuckDB. I'm working actually 1 day a week at MotherDuck, which is a US funded VC-backed cloud service around DuckDB. Also has an Amsterdam office, and they also launched something called Duck Lake, which is a new kind of data lake that leverages database technology to make things smoother. Back to vector. So I mentioned vectorized query processing a couple of times. But I actually also in my title is vector search. So these are two different kinds of vector. So have nothing to do with each other. Actually, even when we introduced vectorized query processing as a term, people thought it had to do with vector processing, so with SIMD instructions or something like that. Has something to do with it, but it's not the same either, because vectorized query processing is more like batched query processing. And yes, that helps using those SIMD instructions. But yeah, vector databases, VV8, Pinecone, Milvus, they are something really different from vectorized query engines. So the vector databases store multidimensional vectors, multi-dimensional, high-dimensional points that people use to represent, well, currently mostly embeddings. So in this talk, I will present some work of done with my PhD student Leonardo Cuffo, and this is called PDX. So what's that about? Well, it's about vector search. So what is vector search? So if you have an embedding model, for instance, something that recognizes pictures, then you can kind of, it has been trained on pictures, then you can show a picture, for instance, and outcome activations. That was what the model will, how the model will see this input. And people, and you can therefore now look at a picture as if it were a multidimensional vector. So all those weights or all those activations that the model produces, together they form a high-dimensional vector of numbers. And yeah, and if you kind of plot a whole database of images in this high-dimensional space, you get lots of dots in a high-dimensional space. It's hard to imagine, but it kind of you can imagine it like this. And then, so if you may have a database of all these of many pictures. If a user query comes, what you could do is you could take that user query, also put it through the model, also map it into this high-dimensional space, and then the question is, yeah, what points are closest? What points in the database are close to this query? So then we get into vector search, and vector search therefore means looking for points that are closest in a high-dimensional space. It's called approximate nearest neighbor search. Approximate because in these applications it's usually not strictly required to find the exact nearest neighbors. The approximate nearest neighbors typically are good enough because the semantics of this is fuzzy anyway. You know, so these numbers are just in fact numbers. So small perturbations do not matter so much. So, and this would then allow you, hopefully, the point in your database that is closest to your query is something that's semantically related to a dog. So that is how a vector search works. So yeah, these systems, they need low latency. They need to store relatively large amount of data. These vectors are large. So high-dimensional, very many models have like 1,000 or 1,500 dimensions. So that makes, if it is 1,000 dimensions, that makes a single vector 4 kilobytes, because usually these things are floats, 4 bytes, okay? But you can also have 10 to the power 5, so 100,000 dimensions in certain models, which makes things harder, bigger, requiring more storage, but also more compute. Because what these vector search systems have to do is they, in theory at least, have to do a lot of comparisons and compute a lot of distances, the query versus the entire database in the worst case. That would not scale so well, but it's a lot of computation. So the use case is information retrieval, recommendation systems, and currently very much RAG. So enhancing prompts, finding semantic matches, injecting information that comes from additional databases into the prompt to make it to make up for lacking knowledge in the training material. So you can bring in data, extra background information in the prompt in order to combat these hallucinations. So very important, and in any kind of approach where you use vector search, you have to do a lot of distance calculations, and therefore you need to do them fast. And for that, on CPUs, people are relying a lot on SIMD instructions. And this is also the area of work where PDX was proposed. So what the basic proposal of PDX is so if you see here a database with 4 vectors, what like PG Vector would do, or what many databases will do, is they will consider a vector a new kind of data type or an object, and it will be a rather large object, like 4 kilobytes, because basically it will see it as one thing, and it will be stored as one chunk of memory, and that effectively is the horizontal layout. It stores all the different dimensions right after each other. So you see here dimension 0 is blue, dimension 1 is orange, dimension 2 is green. So you see blue, orange, green, blue. So if you look at the memory, it looks like this. And what PDX proposes is, what MonetDB proposes and what Vectorwise is and DuckDB does. Why not consider a column-oriented layout also for vector storage? It's a bit more complicated because now a vector is not a single object. You kind of chop it up dimension by dimension. You put all the values for the different images, the blue dimension after each other, the orange dimension after each other, but it can have certain advantages. Advantages in specifically SIMD instructions, because we want to use those. So what can SIMD instructions do? So SIMD instructions, they, in a single instruction, can do an operation on multiple data, SIMD, that's what it stands for. So you can here see what you could use it for in similarity search. So we need to compute the distance, could be the L2 distance, Euclidean distance between a database vector and a query. So what do you have to do? Well, you have to subtract to see the difference on all dimensions. And then, you have the delta, and then you have to square that, so you have to multiply that with itself. That's the green operation. And then you do a sum to kind of sum all those values, all those dimensions together, and then you have a distance. Very, very basic L2 distance. And this would therefore happen in 3 instructions only. And the amount of dimensions that you can address, on AVX 512 would mean that you can do 16 of those dimensions in one set of these instructions. So it could be 16 times faster than doing it without SIMD instructions, which matters. So if you look at how L2 distance calculation looks like, then you get an image like this. What's interesting to see here, I mean, I don't want you to completely understand this, although it's kind of the same story on the last slide, is that the parallelization happens on the dimension. So if you load a SIMD register in the various cells, you have dimension 0, 1, 2, 3, 4 of one vector. What you get if you do the PDX thing, the columnar thing, is that you can parallelize in a different way. What you're going to say is we are first going to compute dimension 0 for everybody. And that means that on the horizontal axis now you fill those cells with different database objects, with different images. So vector 0, vector 1, vector 2, so there's the image 1, 0, 1, 2. So now we're basically going to concentrate first on dimension 0, and we're going to only calculate the distance on dimension 0, and then dimension 1, and then dimension 2. So this has some advantages because there are some data dependencies in the end, which can hinder the SIMD performance. The horizontal kernels need more loads, twice more loads. And there is this reduce step. Reduce step is not so nice for SIMD because SIMD is very efficient when you do things independent in every lane. But as soon as you have an operator that somehow has to cross the lanes, has to sum up everything in the different adjacent cells, that's actually what SIMD processors don't like to do. And that's relatively slow. So we saw by just changing this layout that we get a moderate performance improvement, like 20% for the columnar layout. But that's not all, because another trick that people do in order to try to make distance calculations faster is to try to avoid calculating the full distance. So that's partial distances that are then computed, and partial distances are very often enough to find the best matches. So yeah, we don't need to evaluate all the dimensions. Sometimes a few are enough to solve the KNN problem. There was a paper with a technique called AD sampling that showed how this could be done. So how does that work? So suppose that we here have a database with vectors, and they have been partitioned into clusters, cluster 0 and cluster 1. The idea, this is when you use partitioning, so then you basically put all the images in different clusters when you load the database, and then when a query comes, you look at in which cluster the query falls, and then you start with that cluster, and you only look at a few clusters around where that are nearest to the query, and then you skip already the partitions that are far away from the query. So you might miss actually the best matches. It's approximate near neighbor, but that tends to still work relatively well. Okay, so after inspecting the vectors in C0, so you first do a bunch of work on the first cluster, and then you already have distances, okay, you have calculated the distance of the first cluster, and those distances can become a bound, because anything that's worse than what you already found is never going to make it in the top 10, let's say. So, so when you move to processing the data from cluster 1, you can already use the bound from cluster 0 to prune and then to stop early. So what does that mean? So if you have the horizontal layout, you would actually be doing all those dimensions. You would do them maybe in chunks, because every SIMD instruction does a couple of dimensions in one go. And after every chunk of dimension, after every SIMD instruction, you can already see, is my cumulative distance already worse than the worst of than the 10th position in the top k? Then it will only get worse, because the distance monotonically increases, so it only gets higher. So if you already crossed that point, then this vector is not going to make it in the top 10. You can stop, and basically you can cut short the evaluation. If it's not better, then you just continue, but then and you repeat the process. The problem is that this branch or this testing can also be problematic, especially when these if-then-elses, the CPU will try to predict them, and if you do a misprediction, then you get some penalty. So it can become a bit hairy. So the true power of the vertical layout of PDX, we call it PDX search, is that it really is very flexible in this pruning. So, because now what we are going to do is we are going to do the pruning not on a tuple, on a vector by vector basis, but we're going to race through an entire dimension in an entire cluster. We're going to not stop. We're not going to stop for any traffic lights. We're just going to go on. There are no branches, no tests. But after evaluating a dimension, we do the pruning. So initially, for the first cluster, we don't have a bound yet, so it's kind of processed completely. The first cluster would be the cluster that's closest to the query, but usually you process like tens of clusters closest to the query, so you still have a lot of work to do after that. But you set up a prudent threshold, and that data structure there is a heap. You usually would use a heap, a min heap, to have the easily maintainable top 10. And then for all the other clusters, you would split the work in a warm-up phase, where you start with a dimension, the first dimension, and after every dimension you check. You check if the distances that you computed so far, the partial distances, exceed the threshold. But we will not immediately stop, only after a sufficient number of, here's only one tuple or one vector that's not qualifying. That may not be enough to already kind of cut it short. Only when a lot of them do not qualify, you really stop. So we do 2 more dimensions, let's say, and after 2 more dimensions, almost all tuples have been disqualified. Vectors cannot make it, and then you switch to a different algorithm where you go for individual checks. The few remaining you then check. Okay, but this kind of code pattern is much more friendly. It's less branchy. It has this nice sequential access pattern. It already uses the vertical kernel, which was a bit faster in the first place. So all together, it gets a lot better. So then the differences really pile up, and you get significant acceleration of the distance calculation. So this is PDX is easiest to imagine to integrate in IVF, which is this partitioning. IVF stands for inverted files. People call it IVF. It's one of the 2 main approaches for vector indexes. Although you could also imagine to use it in other data structures like graph-based indexes, because in either of them it boils down to doing a lot of distance calculations, and you can make them faster. So that is. So as long as you have a bunch of neighbors, for instance, in a graph index, you can also imagine using PDX search for it. Yeah, talking about that. So in vector indexes, there is kind of a battle between 2 lines of thought. Some people say graph-based is better, and others say partition-based is better. So yeah, what does it actually mean, those kinds of indexes? So you have a bunch of high-dimensional points. In partitioning, so in IVF, how this works is usually with k-means. So if you want to have k clusters, you first do a k-means on the points. So you get kind of some k representative points that are relatively far each from each other. And then you put every vector in the cluster belonging to where the closest to that centroid of the, so those points become the centroids, the central points of every cluster, and every vector is put into the partition on that basis to the closest centroid. And then you have these, kind of a partitioning of the space in a way. And then when a query comes, you're only going to look in the closest partitions. And the graph-based work, and the most often used term is hierarchical network of small worlds, HNSW. And that is like a graph structure of where you sample the database, and you start with a very, very, very highly sampled database. You navigate through it, and then in the closest point you go down, and then you have a less sampled version of the data. But these arrows down, they are materialized. So you do kind of a very targeted traversal of the space. So the different, the world is split between these. So like half of them use HNSW, the other ones use partition-based. So it's still a kind of a battle of ideas. That is not so, it's not settled yet. Although we think that our work settles it a little bit, hopefully. So for query throughput, graph-based works fastest. Indexing is problematic. These graphs are difficult to construct. Memory footprints of the graphs are also larger and therefore less attractive. Insertions and deletions are also harder in a graph. And filtered search is also more difficult to do in a graph. I will get to that. So this is a bit of the preview part. So in the lab, we have now these results. So when people think about the performance for queries, they tend to think that IVF is much slower. So the throughput of the blue line is much slower than the red line. But with PDX, it gets very close now. So there is not so much of a performance difference. Whereas constructing the index is much cheaper for a partition-based approach. So we do think that PDX pushes IVF to have an advantage over graph-based approaches. So some secret sauce is a hybrid PDX storage where we have the first dimensions vertical and the latter ones horizontal. And actually in k-means, you also can use PDX and to get a very fast k-means algorithm, because k-means is an important component in the cost of the index construction of IVF. Okay, very quickly. So one problem that the field struggles with is filtered vector search. And this is really an area where, that calls for deeper integration in database systems of vector indexes. You cannot really glue the two together. If you do that, then you will not have good filtered search. So what is filtered search? Filtered search is when you are giving an image as a query. You want the closest matches, but in addition, you also have my slide doesn't work. Okay. You also have a explicit condition, like species is dog. Should have been there, but so then you have a mix of a database kind of predicate, a condition, and an image condition. A semantic condition, and combining them that's what people call filtered search, because you have to do vector search, but you also have to apply some database filter. So the problem is if you kind of first use your HNSW index and you get 10 results, and these systems are kind of built to return a few best matching results, then if the selection percentage of that predicate is too low, so you get 10 results, but your filter is 1 in 100, you're likely to end up with 0 results, because none of the things that came back from the vector index from the vector index matched the predicate. So that is post-filtering. Post-filtering has this problem that you run out of candidates because they are eliminated later and then you end up with nothing. And pre-filtering, so first running the database query on your condition, species is dog. The problem is then you have a list of matching whatever rows or something. Then you don't have an index built for that specific subset of rows. So you cannot really use the index, at least not easily. Well, not easy, but maybe difficult. People have proposed kind of difficult stuff. Oh, I will create a separate index for every possible predicate. Yeah, then you can use it, but that doesn't. People would like to have lots of freedom in any database predicate. So then you cannot build an infinite set of indexes, and they're large and they're So it's a difficult problem. Yeah. So this is a problem that is kind of leading vector search people to scratch heads and to redesign their systems. But we argue, well, we should not really. This really calls for integration, deep integration of vector search into database systems. So we should design, or actually redesign, indexes, vector indexes for data systems, leveraging the capabilities of databases, like predicate evaluation, and prevent that we will be reinventing the wheel. Because you get this new class of vector databases, and now that filtered search becomes a thing, they start to become more functional, more complex. And what eventually is happening is the reinvention of lots of stuff that we already have in databases. And that's what this what goes around, comes around, etc. paper is about. So currently we're working on a new DuckDB extension for vector search that can actually excel in this predicate evaluation, and of course it is based on PDX. We have been doing this columnar storage for an IVF. So one of the crucial ideas here is row group driven design and row group driven parallelism, because row groups are the way that DuckDB and many systems organize data. So a row group is a slice of a table. In DuckDB, row groups are 120k rows, and for instance, if you do parallelism in DuckDB, it is row group driven. So typically every thread gets a row group of data to work on. It's also, row groups are also a unit of transaction processing, of checkpointing. So there are many things in the database system that are row group organized. So if you think of, there are some systems that, like Microsoft has developed vector search, and they have support for filtering as well. But what that kind of, how that means, what that kind of, so how that works is that all the data of the database is still inserted in some kind of indexing data structure. So you have one big index that in this case has blue and green dots, meaning they come from the blue and the green row group. So they end up in the same data structure. So they build basically an index. One index for all the row groups. And then search is performed in that. But usually, even if you have functionality that during the searching in the index kind of checks with some bit mask whether a row is included or excluded, it kind of forces that you need to evaluate the predicate fully before you can start the vector search, because these two objects are very differently structured. So in the vector index you can encounter any row at any unexpected moment. So you have to know which rows are in or out before you actually start going in that index. And updates in one row group also will change the entire index, which has write amplification drawbacks. So our idea is to actually go with the row group flow in vector indexing and make a separate index per row group. This has a number of advantages both in the data management like think of transaction processing, checkpointing, that's already happening on a per row group basis. But it also has additional advantages for the creation of the ingest, for instance, of data, because people will write new row groups, don't have to readjust the one big vector index, but they can just create a new vector index belonging to that new row group without touching all of the other row groups. And there are also some additional advantages, namely you can have drift, like the k-means can change. So what are the best centroids? If the data distribution changes and new data is in, one of the problems is that you might actually have to repartition your data because the data is now different. So if you do a k-means for every row group, you will never have this problem. And in fact, your means may be better because they are targeted for the data that's effectively in that row group. But yeah, because people have been addressing the vector search problem from kind of two completely different angles and kind of gluing libraries together, glue a library to a database system is the usual approach that people have. They haven't thought about deeply integrating vector search capabilities inside a database system, which is what this is at least trying to do. So we get faster index construction times because if you write a new row, you just write a new small index, smaller indexes, more targeted indexes, and also automatic parallelism out of the box, because the idea that you do parallel processing in DuckDB for a row group now also applies to vector search. And also skipping. So very important in analytical databases is trying to skip row groups. So now if you have a filter predicate that the min-max indexes, the zone maps tell you will not qualify in a row group, also means that we're going to do less vector search because we're going to skip also probing the vector index of that row group. So that's, so things get eliminated and vector search work is also getting less. Does this work? Well, it is a work in progress. It seems to work. So this is the ingest is actually much faster. Query performance is still being worked on. This is actually the wrong figure because this is for single threaded, and it shows that the per row group is slightly slower. But our results with 10 threads were actually that it actually scales better. So it's actually working. Although this is still not it's unreleased code still in the lab, but it looks really promising. I will come to a conclusion here. So I introduced to you first this idea of columnar storage for vector search. It makes index calculations faster because it produces slightly better SIMD kind of code patterns. But also it enables this column by column pruning, PDX search, that allows to cut the search short really quickly. And that really makes a big difference in distance calculations. And then we are trying to use this new methodology for storing vector data in this new DuckDB extension that is deeply integrated and stores everything row group by row group, which we think is solving a lot of problems both on the data management and on the parallelism and the performance side and on the side of the integration of classical database predicates with image search or with vector search predicates. So we think that's looking very promising. With a lesson to draw that to design these new systems, we should not glue things together, but we should really redesign these indexes to take advantage of the architecture of data systems. And that's it.
Thanks. So it's a really fun tour. So you said some people have previously proposed essentially just like having an index for every possible predicate that you could need. It feels like doing indexes on row groups is essentially that, but just like with a couple kind of less customizable predicates. Is that roughly a correct understanding?
Not really, because what I mean by saying, okay, building an index for every possible predicate means that you would build an index for a query on the column species is dog, but you would have to create another copy, a completely different index when you want to support a query on another column like geography or something. It's really not sustainable. It's not tenable. It's only, you can only do this for a very limited amount of queries. Whereas the row group ID is completely agnostic of whatever predicate you can support. Because what happens in this filtered search is that we will first use fast vectorized query execution to evaluate any predicate, whatever it is, and then use those selected row IDs to prune the results of the vector search. So.
And like in real world data, does that frequently end up like reducing the number of row groups that you have to look at?
No, well, I mean, reducing the number of row groups means row group skipping. So that happens quite a bit, I would say, in analytical queries, because people really also try to optimize the layout of their tables such that these min-max indexes are effective. So, like if you are in Databricks, for instance, there is something called liquid clustering that reorders a delta table such that the min-max skipping gets effective on multiple columns. So those things you will get out of the box in this design.
I'm curious whether this plays extra nicely with embedding models that are trained with the Matryoshka representation learning, where it tries to like compress all the significant information into the first dimensions. Does that help?
There is definitely like the PDX search, where you try to cut the calculations short after a few dimensions. Those kind of approaches, this approach can play well, I think, with the Matryoshka idea, because then you concentrate a lot of meaning in the first dimensions, which would mean, or should mean, that you will get more pruning more quickly, because the information is really condensed in the first dimensions. So we haven't, I think, this is a question that I really should ask Leonardo, because he would be more on topic. He also cites it and talks about it. So, but I think your hunch is correct. Yeah, you.
It's actually a good combination of like SPFresh type approaches for like object store-based indexes, where you combine SPFresh with PDX layout.
Okay, I don't know what SPFresh is. I'm sorry to say.
It's like a way to online update indices, object storage, and rebalance the clusters for things. We're smart about the IVF index.
Okay, yeah. Well, I mean, PDX combines really well with IVF indexes, so that.
The nice part is if you have an object storage, you can like page in only the first 3 dimensions.
Oh, okay. You mean like S3 storage? Yeah. Eventually, I mean, we would like this to work on object storage as well. So we, like I mentioned, Duck Lake, for instance. So we would like to have this extension work on Duck Lake as well, which is interesting because in an object, in like an iceberg kind of lake, the data is stored in Parquet files. But what we are thinking of is actually storing the index, so the vector index, in DuckDB, which if you know about Duck Lake, it kind of can be used to hold all the metadata of the data lake. So you get kind of hybrid storage. You can put indexes in the metadata database and the real data in the Parquet files. It's a bit our play there.
I also wanted to ask about object storage because of Turbo Puffer. So
yeah.
I mean, at least they claim they're the first one. Probably not true given that this.
I think that was also my understanding that Turbo Puffer is at least the first the system that has made a success out of vector search on object storage, and they are using the IVF approach. I think yeah. Okay, yeah.
But I'm guessing they're like row-oriented and not column, or are they also?
I actually don't know how they store the vector information itself, but I would expect it to be row-oriented at this moment. But yeah, we might take a look at PDX. It's open source. Yeah.
You said you've sort of been working on this code, getting it ready. Like, what's the current status of like what can we try out?
Currently, I think if you go to GitHub CWI-DA, database architectures /PDX, you will find there open source PDX implementation with Python bindings. So that's not integrated in DuckDB yet, but you can definitely play with it from Python. And the extension is work in progress.
If we have a bit of time, can you re-explain the non-IVF approach, the graph-based? I didn't quite get it. The alternative.
Oh, HNSW. Yeah. So HNSW is a graph. So it is a bit like it's like a tree. Where is it? With more edges. It's kind of a three-dimensional tree. Here it is. So you see at every level you see a graph. So you have nodes. These are basically the vectors or the images, and they have neighbors, which are the k nearest neighbors. That's the idea of the graph. So the neighbors that remain in the graph, or the only edges that you have between them, are the nearest neighbors. So you do not necessarily have to calculate all the distances. You already know who the nearest neighbors of that node are. So that the materialization of those nearest neighbors is the big win of the index. And the other problem is, of course, you can have very, very many vectors. But you need a starting point, and therefore you have multiple hierarchies, which are basically subsampled data sets. So it's a very, very highly subsampled on the highest level. You first do a search there, which is basically walking around like greedily to your nearest neighbor. And then you are in a node or some nodes, and then you go down, because the same node that exists on the higher layer also exists on the lower layer. But on that lower layer there are more nodes, because the sample is larger. But the sample on the middle layer includes everything that's on everything on the higher layer is included in the lower layer, let's say. So you can go down. So you have a node that looks like quite near. Then you go down, and then you have more resolution. And then you look, okay, on this higher resolution, the second layer, I have new neighbors. You check those out, and then you go down again. This process can repeat. And in the end, you do a very targeted walk towards what hopefully are your nearest neighbors.
Yeah. Could you combine this with the other approach where you have, I thought that originally the layers were kind of your canon, and you could materialize the nearest neighbors into.
There are at least 1,000 different proposals for vector search indexes, and some of them try to combine IVF and HNSW. Yes, both ideas. Yes. Yeah.
Thank you.